myprojectbazaar.com. Our product title is voltage sag and swell compensation using isosource inverter based dynamic voltage restore. Let us see about the abstract of our product. In this proposed implementation, we changing the circuit design for the corresponding output. So that is the client requirement. So that only we did in this process, and also corresponding output waveforms only here we presented. And in this proposed implementation, abstract is presents the modeling and simulation of a dynamic voltage restorer as a voltage sag and swell mitigation device in electrical power distribution networks. The dynamic voltage restorer with its excellent dynamic capabilities, when installed between the supply and a critical load feeder, it can compensate for voltage sag and swells, restoring line voltage to its nominal value within few milliseconds, and hence avoiding any power disruption to the load. A new topology based on isosource inverter is presented in order to enhance the voltage restoration property of dynamic voltage restorer. Isosource inverter would ensure a constant DC voltage across the DC link during the process of voltage compensation. The modeling of isosource based dynamic voltage restorer is carried out component wise, and their performance are analyzed using MATLAB software. The simulation result shows that the control technique is very effective and yields excellent compensation for voltage sag swell mitigation. In this proposed implementation is done in MATLAB simulating environment. Next we see about the flow diagram of our process. In this proposed flow diagram, the source is a AC supply, and also that source is a single base AC source, and that source is fed into the PWM inverter using of isosource inverter through a line impedance and series transformer and the filter circuits, and also the PWM inverter is getting the supply from the storage unit in the through a DC link, and finally that supply voltage is fed into the load. In between, the DVR process is done in the filter circuit across the transformer side. So modern power system or complex networks where hundreds of generating stations and thousands of load centers are interconnected through long power transmission and distribution networks. The main concern of customers is the quality and reliability of power supply at various load centers. Even though power generation is most well developed countries is fairly reliable, the quality of supply is not. Power distribution system should ideally provide the customers an uninterrupted flow of energy with smooth sinusoidal voltage at the contracted magnitude and frequency. However, in practice, power system, especially the distribution system, have numerous nonlinear loads which are significantly affect the quality of power supply. As a result, the purity of waveform of supply lost. This ends up producing many power quality problems. Apart from the nonlinear load, some power system events, both usual and unusual, could also inflict power quality problem. The consequence of power quality problem could range from a simple missense flickers in electric lamps to a loss of thousands of rupees due to power shutdown. A power quality problem is defined as any manifested problem in voltage or current of leading to frequency deviation that result in failure or misoperation of customers' equipment. Power quality problem associated with an extensive number of electromagnetic phenomena in power system with broad ranges of time frames such as long duration variation and short duration variation, and other problems are rectified using of the DVR method in between parallel connected the shunt active filters and other active filters. That is corrected the sag and swells and also restore the original value of the source voltage and fed to the load also. Next we see about the running process of our product. In this proposed implementation is done in the MATLAB simulating environment. First open the MATLAB window and create a new model file. After creating that new model file, we are arranging the elements as per the given flow diagram from the simulating library browser. In the simulating library browser, two kind of toolbox we used. One is the simple power system toolbox, another one commonly used toolbox. From that toolbox we getting the elements and then arranging that elements as per the given flow diagram. And also in this process we design two kind of process. One is the sack oriented simmering, another one swell oriented cooling. So first one we see the sack oriented process. So sack means the voltage is reduced using of nonlinear load due to the some seconds only. So in that seconds the voltage is injected to increase the level at the normal source level. So first one is the uncompensated voltage, then second one is the injected voltage, third one is the compensated voltage. So this is done, and this is the input source of waveform, this is the uncompensated voltage waveform, and this is the compensated waveform, and this is the DC source value of the using the sack compensator, sack and swell compensator input side. And next one is the swell process. In the swell process we know that when the nonlinear load is connected to the source, then the voltage level will be increases using of them some elements. So in that condition we using compensator, swell compensator. So in that swell compensator injected voltage, in that voltage that reduce the uncompensated voltage level into the compensator. These are the variations of the uncompensated, injected and compensated value. And next one is the output of the injection current, and this is the input, and this is the input of the DC source compensator voltage. Thank you for watching this video.